All right, guys, today we are talking about implicit differentiation and a lot's changing simply based on the form of our expression. So here on the left, we have an equation written as x times y equals 6. We call this written implicitly, meaning that the x's and the y's are mixed together. If I were to divide by x to get the y by itself, we would call this an explicit expression because the y is on one side, the x is on the other. So all implicit means is rather than getting y by itself, sometimes our x and our y are mixed together, but we still need to be able to differentiate. And really that comes down to the complexity of the problem. This one right here, xy plus y equals x, that's an implicit expression. But when I factor out the y so that I end up with y times x plus 1 equals x, I can divide by x plus 1 and I can make it an explicit expression. The problem is when you get to these ones. This one, x squared y plus xy squared equals x plus 1, really difficult to do. The one on the bottom is impossible because one of our y's is stuck inside our sine function and the other one is outside. So this is kind of what we've done before. We've stuck with this right-hand side, and today we're going to start working on these things on the left, just so that we don't have to worry about always solving for y. Sometimes we can, and it's easy to do, but a lot of times it's difficult to do that. So what you've seen up to this point, when I've had something like y equals x squared, we've said, okay, take the derivative and we write it as y prime equals 2x. Well, what's really happening here that you're not seeing, that we don't always write, is when we take the derivative of y on this left-hand side, what we're actually doing is rewriting it as dy dx. The derivative of y is written as dy dx, but we kind of use y prime as shorthand. So what you're going to see a little bit more this time is this version of it. You're going to see the dy dx. Technically on this side, because we're differentiating with respect to x, which is all we really do in Calculus 1, technically on this side, I get y prime equals 2x or dy over dx equals 2x. Technically, there's a dx over dx, but dx over dx is 1. So we don't ever write it because there's no reason to. It just cancels itself out. It goes away. It's messy. So we usually just keep it written this way. But you just need to realize dy dx is the derivative of y. So what this says up above is when you differentiate terms, when you only have x, we just do what we normally do. So when I just have x squared, I treat it as normal. But when you differentiate terms that have a y, we're going to have to use the chain rule. And here's what that looks like, just to kind of give you an example. So this problem down here, our example says y cubed plus y squared minus 5y minus x squared equals 15. I don't even know where I would begin trying to get y by itself. It's probably possible, but right now I've got a cubed, a squared, and a y. That's a lot of work to try and differentiate or try to solve this for y first. So we have another way of solving this differential. And now here's the steps that we're going to go through, and we'll do them one at a time. But the first thing that we're going to do is differentiate both sides of the equation with respect to x. So following step 1, I'm going to differentiate both sides, even though y is not by itself. And the way that I do that is this y cubed, I treat just like I would if it was an x. I'm still going to bring the 3 in front, and I'm going to write y, and I'm going to reduce the 3 down to a 2. It's still 3y squared, but I differentiated y. And so I have to add this dy dx to it. It's not just 3y squared, because technically we're kind of using the chain rule. The y is a function inside of this, So I have to take the derivative of y, which is my dy dx. So then I'm going to add y squared. The derivative, just like if it was x, is 2y. But again, because of this y that's on the inside, I have to multiply by the derivative of y, which is dy dx. And then again here, negative 5 times y, the derivative of negative 5y is just negative 5. But I had to take the derivative of the y, which is dy dx. And then the minus x squared, because there's no y involved, I treat that like I normally would, a negative 2x. I don't write the dx over dx because it just cancels out. There's no reason to. And that's all going to equal, when I take the derivative, since I took the derivative of the left, I have to take the derivative of the right. And the derivative of 15 is just 0, which is kind of nice because that cancels itself out. So that's step 1 right there in red. We did step 1. We differentiated both sides. Just anytime we saw a y, we had to add that y prime or dy dx. Now, I see a lot of people that would have written this as 3y squared, and then instead of dy dx, they put y prime, and then they put 2y, y prime minus 5y prime, minus 2x equals 0. Here's my issue with writing it this way. Are those y primes or are those y to the first power? That bothers me because it's really easy to mix up what's what. So when I'm doing implicit differentiation, I usually will use dy dx and not the y prime because I want to be careful not to mix those two things together. But it means the same thing. The dy dx, the y prime, same meaning there. So step 2 is to collect all the terms that have a dy dx on one side and move everything else to the other side. So in this one, it's not too bad because this has a dy dx, this one has a dy dx, this one has a dy dx. All I have to do is move this negative 2x by adding 2x to both sides. So I still have 3y squared dy dx. And I already know there's a whole bunch of you that are going to prefer y prime because it's a lot less writing to do. And that's okay. You can write y prime. Just be careful not to mix that up at any point thinking it's a y to the first power. So this, I moved to the right-hand side. So now I've got a 2x over here. Now step 3 wants me to factor out dy dx out of everything on this left-hand side. So all of these terms have a dy dx. So I am going to factor that out. And I don't want to use that color. So let's go back to red. So I'm going to take that dy dx and I'm going to factor it out. So what's left over is my 3y squared plus my 2y minus my 5. And that's going to still equal 2x. So all I did was factor out that dy dx. Now to get dy, step 4 is getting dy dx by itself. So I need to get rid of this big parenthesis. So dy dx is being multiplied by that parenthesis. So all I have to do is divide both sides by 3y squared plus 2y minus 5. So this side needs to be divided by 3y squared plus 2y minus 5. So when I do that, I end up with dy dx is equal to 2x over 3y squared plus 2y minus 5. Which is the same thing as saying y prime is equal to 2x over 3y squared plus 2y minus 5. I'm not going to use this one, but you are welcome to, as long as you know what's going on. Now, a lot of times these problems are going to ask for the slope. And in this case, normally what we've done up to this point is it's asked us things like, what's the tangent line at a certain point or the horizontal tangent line? And at this point, we've only had x's. So it's given us a point and said, okay, at the point 2, -4, what's my slope? Well, I don't have just an x in here. So if I need to find the slope, if you need to find the slope, you're going to have to plug in x and y. You've got to use both terms from your coordinate point. You have to plug in the 2 for the x's and the -4 for the y's. We're not going to do that on this problem, but just know when you look for the slope, you can't just plug in x because there's also y's that you need to find. Okay, so let's just do examples here. So find the points where the curve has horizontal and vertical tangent lines. We've done quite a few problems like this before. Remember, a horizontal line happens when my slope is equal to 0, and a vertical tangent line happens when my slope is undefined. It's when my function isn't defined because there's that vertical line, and when you have a vertical line, you don't have, your slope is infinity. It doesn't exist, so it's undefined. So what we're going to do first, looking at this, it's almost a circle if it wasn't for this 4. This is actually an ellipse. It's kind of like a smush circle or an elongated circle, like an oval. But let's go ahead and, rather than try to get y by itself, because then I'm going to have to use 2 different formulas, let's just use implicit differentiation. So to find the derivative, I'm going to take the derivative of both sides. So for the left side, my derivative, I get 2x plus, I bring the 2 down to the 4, I get 8 y to the first power, and I'm not going to write a 1 because someone's going to mix that up with y prime. I'm going to just leave it as y. But don't forget that chain rule. Because I'm taking the derivative of something with y, I've got to write dy dx. And that's going to equal the derivative of 4, which is just 0 again. So that was step 1. Step 2 wanted us to get dy dx terms by themselves. So I'm going to get rid of this 2x by minusing it to both sides. So I end up with 8y times dy dx equals -2x. And then step 3, we wanted to get, we normally, well, I guess we would factor out the dy dx, but there's only one term. So step 3 and 4 kind of go together on this one. I'm just going to get rid of the 8y. So I'm going to divide by 8y, and I'm going to divide by 8y over here. So my function becomes dy dx is equal to -2 over 8, just becomes -x over 2 over 8. That leaves me a 4 and a y on the bottom when I simplify that fraction right there, which is the same thing as saying that y prime is equal to -x over 4y. So this is my formula for slope, right? That's my derivative. It just is written in a different way. So what I need to find is, first of all, my horizontal tangent line, which means I need to figure out what happens when this right here, my slope, is equal to 0. So to get my slope equal to 0, I'm going to say 0 is equal to -x over 4y. So let's go ahead and, well, I guess what's going to, if I'm looking at this, what's going to make this equal to 0? Because I can't just, I can times by 4y, but I'm going to end up with just my -x, right? So what's going to make this 0 is if my x is equal to 0. That's what makes this fraction 0. So if my x is equal to 0, then my fraction is going to become 0. So when I plug that in, when my x value is 0, I need to know my y coordinate because it wants the points. So I know that when x is 0, this function is going to have a slope of 0. But I need to know what the point is when that happens. So my x value is 0, so I plug it into my original equation. So 0 squared plus 4y squared equals 4. So that goes away. I can divide by 4 on both sides. Y squared equals 1. So y equals plus or minus 1. When I take the square root of both sides, I've got to take the plus and the minus of 1. So what that means is I actually have 2 points. When x is 0 and my y is positive 1, and when x is 0 and my y is negative 1. At those 2 points, I'm going to have a horizontal tangent line. Now, my vertical tangent lines happen when my 4y, when my number on the bottom is equal to 0, I have that asymptote. And so that's where I have an issue, and that's what I want to know. What makes my bottom 0? Well, 4 times y being 0 means that y has to equal 0 to make that happen. So when y is equal to 0, I get vertical tangent lines because it makes my function undefined at that point. So I know my y, but again, I've got to plug my y back into the original function to figure out my x value. So I get x squared plus 4 times 0 squared. That's not a 40, and that equals 4. So that all goes away. X squared equals 4. So when I take the square root of both sides, x is equal to a positive 2, but it's also equal to a negative 2. So again, I have 2 points at 2, 0, and at negative 2, 0. This is going to happen, which is kind of cool because that gives me 4 points. So I can actually graph this ellipse now. One of my points is 0, 1. So I've got 1 point right here, and 0, negative 1. I've got another point there, and 2, 0. So I got to go over 1, 2. And I got to go to the left, negative 2 and 0. Wow, those went a lot further out. But what you end up with is that oval, that ellipse that's a little bit further to the left than it should, but that's just a drawing mistake, not a math mistake, right? So those are the 4 points that we would be interested in. These are my horizontal, and these are my vertical. And if you look at the picture, there's your horizontal tangent lines, and there's your vertical tangent lines. So that makes sense. Okay, moving on. A few more examples. This is one, I don't know if we've talked about this yet. At least this form of it, d squared y and dx squared. What that actually means is it's kind of like when we would find the derivative, we would call it y prime. Well, this is taking the derivative of the derivative, or we would call it y double prime. And the way that we're going to do that is we're going to find the derivative, and then we're going to take the derivative of our derivative. So with that mouthful, let's just start. Let's find the derivative of x squared plus y squared equals 36, which that's just a circle. And I believe the radius should be 6, right? Because our this number on this side would be our radius squared. So when I take the derivative, x squared, the derivative is 2x, plus the derivative of y squared is 2y. But don't forget, we've got to put a dy dx because we're taking the derivative in terms of x. And then the derivative of 36, again, that's just 0. All right. So let's get all our dy dx's on one side. So I'm going to minus 2x. So I end up with 2y dy dx is equal to negative 2x. And then to get the dy dx by itself, I'm going to divide by 2y and divide by 2y. So I end up with dy dx is equal to negative 2 over 2 is just negative x over y. Now, we've got to be careful because before you do that second derivative, I've seen people try to do the derivative up here when it's written like in this form right here. Don't do that. Get the dy dx by itself. It is so much easier to take the derivative, the second derivative, when it's written in this form. Because now, when I take the derivative of the left side, the derivative of dy dx, remember that's just y prime. The derivative of that is just d squared y. and dx squared. Okay, that's just my derivative of my derivative. And then on this side, to take the derivative, we have to use the quotient rule, because we have two different functions there. So my quotient rule tells me that I need to, we're going to treat this like the top, of course, and this is going to be our bottom. So the derivative, and I'm going to kind of snag that negative and apply and make it stick with the x just to make this a little bit easier. So my derivative of the top, so the derivative of negative x is just -1. And then I have to times that by the bottom, which is just y. And then I'm going to subtract the derivative of the bottom. The derivative of y is just dy dx. That's its definition. The derivative of y is y prime. It's just dy dx. Technically, there's a 1 in front, but I mean, you can write that if you really want to. So the derivative of the bottom multiplied by the top, multiplied by that negative x. And all of that is going to go over the bottom squared. So we get y squared there on the bottom. Now, we have a little bit of an issue because I don't want to leave a y prime or a dy dx in my function. See how I have this dy dx? I don't want to leave that there. So I need to get rid of it. Well, maybe let's clean this up just a little bit first. So let's make this equal. The -1 times the y becomes -y. A -1 times a negative x just becomes a positive x. And then we have dy dx. And that's all over y squared. So we just forgot to simplify right there. So in this form, still, we don't want dy dx. I need to get rid of it. So what I'm going to actually do, I'm going to replace this dy dx with what I know it's equal to. You've kind of done this back in math 2 and 3. Instead of a dy dx, I know that dy dx is equal to -x over y. I already figured that out. So I'm going to actually plug that in for my dy dx. So my equation becomes -y plus x being multiplied by -x over y, all over y squared. And now I just have to simplify. So I get -y. X times -x is going to give me a -x squared. And I still have the y on the bottom. And that's all over y squared. And a lot, like on the free response, great. I love that answer. Nothing wrong with that. But sometimes your multiple choice is going to want you to go a little bit further, and it wants you to simplify that ugly fraction, because we don't just have a fraction, but we have a fraction on the top. And the easiest way, the way that I like to do it, I'm going to move over here so I have a little bit more space. If I have -y minus x squared over y squared, I want to get rid of this fraction. So what I'm going to do is I'm going to multiply everything on top by y, which means I have to multiply everything on the bottom by y. But the reason I want to do that is because when I times the y right here by the -x squared, the y on the top and the bottom are going to cancel. And then I have to times the y by the -y. So that just gives me -y squared. And y times -x squared, and let's write that out. That becomes -x squared y over y. But those are going to cancel. So I get -y squared minus x squared on top. And on the bottom, I just have y times y squared, which is just y cubed, which gets rid of that fraction that we had on the top. Technically, it's correct, but on the multiple choice, I doubt they're going to leave it in that form. They're going to probably simplify it a little bit further. And we should probably finish writing that out. That equals d squared y over dx squared, or it equals y double prime, which is not to be confused with y to the second power, okay? Or to the 11th power, sorry. Let's do a couple more examples. I'm going to speed up just a little bit. Our video is starting to run a little bit long, but let's find the tangent line at the point 1, 1. So remember, to find a tangent line, we need a point and we need the slope at that point. Well, we already have the point, so we just need to find the slope. So we use the derivative to help us find the slope. But our function is ugly. I mean, this is really messy. On this left-hand side, we're going to be doing implicit differentiation on both sides. Over here, we've got the chain rule. On this side, we've got the product rule. But let's start working through that one. Okay, so starting with the left-hand side, I've got to take the derivative of the outside. So I'm going to bring that 2 down. And I've got x squared plus y squared on the inside. And this technically goes to the first power, right? But because of the chain rule, I have to multiply by the derivative of the inside, which the derivative of x squared is just 2x, but the derivative of y squared is 2y dy dx. We can't forget that dy dx. So there's my left-hand side. I think we're done there. That's equal to our right-hand side. I've got 2 functions right here being multiplied. So I'm going to use the product rule. So I take the derivative of the first, which is 8x, and I times that by y. And then I'm going to add the derivative of the second. So the derivative of y is just 1 dy dx. And I multiply that by 4x squared. Okay, so I know this looks really messy. And it wants us to factor out, we're not done with the derivative formula. It wants us to factor out the dy dx and move everything to one side. And that's a lot of algebra. But I already know my point that I want the slope at. I already know that my point is 1, 1. So before I find the slope, before I simplify this function, I only care about that function at this point. I don't care about that function in general, so I'm going to plug in the 1, 1. So I'm actually going to plug in 1 squared plus 1 squared. Because my x and my y are just 1, this becomes 2 times 1 plus 2 times 1 times dy dx is equal to 8 times 1 plus 1 dy dx. We don't really even need that 1, do we? Multiplied by 4 times 1 squared. So this just becomes 2, 1 squared plus 1 squared. So 2 times 2 becomes 4. The inside of this parenthesis, I've got 2 times 1, which is 2, plus 2 times dy dx. So let's write 2 plus 2 dy dx. I'd love to get those 2's spread apart, but not quite yet. 8 times 1, that's just 8. 4 times 1 squared just becomes 4 dy dx. So I know I did that simplifying really fast. Pause the video, excuse me. And if you need to go back and follow that a little bit slower, you are more than welcome to. But from here, this makes it a lot easier to get my dy dx by itself. Okay, so I'm just going to distribute this 4. Let me change colors here. I'm going to go ahead and distribute that 4. So I end up with 8 plus 8 dy dx is equal to 8 plus 4 dy dx. See how much easier this is than trying to FOIL all this stuff out. So let's move this 8 over to this side, and I'm going to move the plus 4 over to this side, which means I need to minus 4 dy dx. And I need to minus 8 from both sides. So 8 dy dx minus 4 dy dx's is just 4 dy dx's. And that's equal to 8 minus 8, which is just 0. So all that work to find out that when I divide by 4, my derivative at that point, my slope is just 0. That was a lot of work. So at the point 1, 1, my slope is 0, which means that's going to be one of those horizontal tangent lines, okay? But it actually wants the tangent line. It wants the function. or the formula. So remember, that's y minus y1 equals m times x minus x1. So y minus my y value, 1, equals my slope, which is just 0, times x minus 1 again. Well, this is all just 0. So y minus 1 equals 0, which means y is equal to 1. And that's my tangent line, which makes sense because if my slope is 0, that means that at that point, at 1, 1, whatever's going on with this function, my slope is 0 at that point. So that means it's changing direction, and y equals 1 is just going straight across. So that makes sense that that's the answer that I got. Okay, one more. Now that we know cosine and sine and all these trig derivatives, let's go ahead and use them. Cosine of x plus sine of y equals y. We're not even going to come close to getting y by itself, so we're going to use implicit differentiation. So I'm going to take the derivative of both sides. The derivative of cosine of x, if you remember, is just negative sine of x. And then the derivative of sine of y is cosine of y, but I need to remember to multiply by the derivative of the inside, which is y. Well, the derivative of y is dy dx. But be careful, that's not multiplying by y, that's multiplying by the cosine of y. Don't mix those two up. And that's equal to the derivative of the right side. So the derivative of y, well, that's easy, that's dy dx. So when I move my terms around, let's go ahead and, I don't know, let's just minus the cosine y dy dx from both sides. Then I don't have to move two things. So I get negative sine of x equals dy dx minus the cosine of y multiplied by dy dx. Well, both of these terms have a dy dx, so I'm going to factor that out. Dy dx leaves me with, oh, not an equal, yikes. Dy dx is what I'm factoring out, and I'm left with 1 minus cosine of y. Because I pulled both of these out, and that's equal to negative sine of x. Now to get rid of my dy dx, I'm going to divide by 1 minus cosine of y on both sides. So I end up with negative sine of x over 1 minus the cosine of y is equal to dy dx. So I've got my derivative by itself, at least my notation, and this is the formula for that derivative. So that would be my final answer.